Hello everyone. So let's get started. Welcome to our session to an introduction of Java's new concurrency model and pitfalls. My name is David. I am a software developer in the Netherlands for around 6-7 years now at Team Workstars, and I'm doing this presentation or this session together with my colleague Ron, who's sitting there, who will tell you everything about scoped values in a bit. But we have a lot of topics to cover today, so let's get started. So today I will start with the current situation. What kind of threads do we currently have in Java? And how do we use them? Then I will slowly go into what are the problems, what are the bottlenecks, and then we will slowly go into virtual threads. And with virtual threads, of course, we get those scoped values. And after we have virtual threads, which, well, famously you can create many of them, as we will see, you will start wondering, how do I manage the lifetimes? And then structured concurrency comes into play. So we will cover the entire lifetime of your virtual threads during this session. But before I start, just a word of caution. Some of the things are still a work in progress. With Java 21, which will be released in September, you will get the virtual threads. They will become mainstream. So the things you will see with virtual threads during this session, it will all work when you have, well, Java 21 later this year. But for example, these scoped values and the structured concurrency, they are still very much in development, which means some things, some method names, some return values, they might still change, but the ideas behind them will be the same. So while some small things might change, you still know the ideas and why they are there to begin with. So let's start with an easy one. Who has done something like this before? Just created a single thread inside Java. That are a lot of hands. This is great. So what happens here is that we just create a new thread inside Java. I call the thread constructor. And at that point, my application is going to talk to the operating system and ask, can you create a just a thread for me? And the operating system will be like, yeah, I can do that for you. I will reserve some memory for it. And then you have your thread inside Java. Because a thread in Java is just a very thin wrapper around a thread that is managed and scheduled by the operating system. So every time I do this, I have to go to the operating system. That takes some time. I have to allocate some memory, which also takes some time, and some memory, which aren't really nice things. And that's why we consider these threads to be very expensive, because of the memory and time consumption that are associated with them. So when I have my thread inside Java, I just call start, and it will start running. Easy peasy. And then this is the easiest way of just using threads. When I have a task, I want a thread to perform that action, and I'm just no longer interested in that thread, and it can just go to the garbage collection. But that isn't a very, well, convenient way for the system, because every time I have to create a thread, I have to go to the operating system, only to be disposed later. So while this is a very easy way for us to program our applications, it doesn't make the best use of the resources that are available to us. So, and that's where the executor services come into play. Since Java 5, you are encouraged to use the executor services instead of the thread class directly. So with a thread, with an executor service, you just have a simple pool of threads, just like this little blue box, which has 3 threads inside of it, and then I submit some tasks. So when a thread is available inside that pool, it will pick up a task, it will start running it until it's done, and then this thread will be put back inside the pool, and it will pick up another task, which is really great, so I don't have to create new threads every time, and Java will all take care of it for me. But there are also some downsides. For example, the thread leakage, the leakage of your thread locals. Because if you have a task that sets a thread local variable, and it gets put back inside the pool, but you forget to unset your thread local, then this thread local variable will still be available to other tasks. So at that moment, you are leaking your local variables into other tasks, which is a big no-no. Or, for example, the blocking. If you have a task that goes to a database, for example, and you have to wait. At that point in time, your thread is just also waiting. It's just being blocked, and it could do better stuff in the meantime, really, like picking up another task or do, well, anything, just not waiting. So the executors, they make it a little bit better for the developers. It's easy to use, makes better use of the resources, but it's still not quite there yet. And that's where async programming comes into play. With async programming, you try to, well, make better use of the resources, and it is very good at it, because you try to avoid the blocking. But in my opinion, it is very hard to write. It's even harder to read, especially 2 weeks after you wrote it. And it's kind of hard to debug, because the whole JVM in Java is really built around those threads. And that's where virtual threads come into play. Virtual threads are just an alternative implementation of the thread class. So the current threads that we have, they won't go away. We just get a new flavor. And the best thing about them is that the operating system doesn't know anything about them. So when I create a new virtual thread, I am not going to the operating system. I just stay in my safe application, and I will just I'll ask JVM, can I create a thread? That's very fast. And the best thing about them is that their stack now also lives inside the heap, which means that the JVM in Java can access it. So every stack can start out very small. With the normal kind of threads, the ones that we currently have, we have to reserve a megabyte just to have it, because we can't change it anymore later in time. But with the virtual threads, because their stack lives inside the heap, we can just start out very small and can grow and grow as needed, or just shrink if we don't need that much memory anymore. And because they are very quick to create, we don't have to reserve that much memory for them, just a few bytes. We consider them to be very small, which gives us a reason to go back to a very easy way of programming. Just create a virtual thread when you have a task for it. And you can create thousands of tasks, or you can create thousands of virtual threads for each task that you have. And that is what I did. I created a small application which just started up a bunch of virtual threads, or platform threads, the threads that we currently have. And I was wondering how much memory is actually being used. So I started out with one of each, and even though it's very hard to see, even this close by, you can tell that the platform threads use a little less memory than virtual threads when you just have 1 or 10 of them. Because, well, they are a little bit cheaper when you have a small number of them. And even at 100, you see that the platform threads finally start using a little bit more memory. But then you have to tell your customer, or your current company, can I rewrite everything to virtual threads just for the tiny bit amount of memory usage that we will use less? Yeah, that's not going to sell. But when you have 1,000 of them, or 10,000, or even more, then you will see that virtual threads really start to show their their benefit, because their power really lies inside their numbers and their memory usage. Because as you can see, you can just create 100,000 of them, and it will use just a little bit over 225 megabytes of memory. And the platform threads, well, they just crashed. So you could also consider that to be very memory efficient, but you also don't have an application. So that is enough of the slides. So let's go to a demo, because the best thing is just showing how stuff works. So the first question, is this readable for everybody in the back? I see thumbs up. Then I will continue. So as I've said, the virtual threads are just an alternative implementation. So I can just use a thread instance to store my virtual thread. But instead of using the thread constructor, I'm going to use a static builder method called the start virtual thread. And as the name does suggest, it will create a virtual thread and start running the task as I gave it. So I will give it the print task. And then I will call the join on my virtual thread to give the chance to print something to the console. And if it runs, well, it prints hello jcon. Oh, it's a bit slow, but it prints hello JCON, which is really nice. So as you can see, it's just very easy. There isn't a lot of API changes that you need to know to start using virtual threads. Just this one method. But as I've said, well, let's show you something else instead, is that we now also get a builder method. So using something like the off virtual, you can also see that I can use the builder to create the current threads using the off platform. But for the demo, I'm going to use the off virtual to create a virtual thread. And then I can set some properties, like for example, the thread name. I'll just call video.thread and give it an unstarted task, so I have to start the thread myself a little bit later. And then I can just call vt.start. And then I created a virtual thread using the builder method. But since Java 5, we are encouraged to use the executor services. So let's see how that works. So I'm just going to create an executor service. Using the new virtual thread per task executor. And as the name does suggest, it will create a new virtual thread for each task that I submit. And as you can see, for the people who are familiar with IntelliJ, it gives me like this orange type hint. It says you can improve something or you did something wrong. I believe it's both. But with Java 21, the executor services also extend the auto-closable interface, which means that I can use it inside a try with resource statement, which is really nice. So I don't have to close my executor services myself, but Java will take care of it for me. And then I can just do simple stuff like submit a print task. Let's do it 3 times. And just like that, I have 3 virtual threads that each print something to the console. And I don't have to call a join on each of those virtual threads anymore. All is taken care of me. So before I can exit this try, all my virtual threads have to be finished running, which is really nice. So let's do something a little bit more exciting. And let's create, well, 10,000 threads, because we can. That's maybe a little bit too much for the console. So let's just create 10,000 threads that each will wait a second, just to show you that it is possible to create that much virtual threads on just a laptop. And just like that, it finished. So that means that each of my 10,000 virtual threads has started, it was created, it waited a second, and then it got executed and it was done. So let's go back to the slides, because I just created 10,000 threads, but as you can see, I just run it on a laptop which doesn't have 10,000 cores. So how do these virtual threads really run in the background? So how does it work? So I just created a bunch of virtual threads, and these virtual threads run on what is called a carrier thread. And a carrier thread is nothing more than just a normal platform thread that we already are using, but it's designed to run virtual threads instead. So how does each carrier thread know which virtual thread to run? So each carrier thread gets its own queue of virtual threads it needs to execute, and every time a virtual thread gets blocked, it will switch to another virtual thread. And if one of the carrier threads is done running, runs out of its queue, so there's no virtual threads left, it will just steal a virtual thread from another queue, because it's using a work stealing scheduler, and the carrier threads run in a fork join pool. So this is how it really works. But then how does the carrier thread know when it needs to switch from one virtual thread to another? And that's done with mounting and unmounting. So here I have this simple carrier thread, and it is running this virtual thread, and it's, well, happily running. Everything is nice. and then it encounters a blocking method and my virtual thread is blocked. When my virtual thread is blocked, its stack gets copied back inside the heap, and the new virtual thread will take its place. So the old one goes back inside the heap, and the new one from the heap will be copied to the carrier thread, and the carrier thread will continue running. So the best thing about this is that while my virtual thread is blocked, it's just waiting and being blocked inside my heap where it can't do any harm, but my carrier thread is always running, well, some work. So this very expensive resource is always doing something, which is really nice. And as I've said, well, when you have blocked, it will switch, but it won't happen every time. For example, not every method is ready yet for this, well, blocking and switching to new virtual threads. For example, if you have a synchronized block, a object.wait, you make a call to native code using GNI, and even certain file system operations cause your virtual threads to be pinned. And when it pins, what it means is that it won't be unmounted from the carrier thread. So when I do make a call to a synchronized block, my virtual thread is pinned, it won't move from my carrier thread, and another can't take its place. So if you are encountering pinned virtual threads, it may harm your scalability of these virtual threads. So that brings us to the pitfalls, because you can't use them in every use case. For example, if you have a long-running calculation on your virtual thread that never gets blocked, then you won't get the benefit of virtual threads, because if it's not blocking, then it will never switch to another one. So in those cases, it's better to use, well, just regular platform threads. Almost not blocking. So if it's just a short operation, it's fine, because for example, if you just have to synchronize blocking, you do just a very, well, small method, just just very quick, then it's all fine. But if you have something, how do I say it? If you really want the scalability of the virtual threads, then doing long-running calculations on them wouldn't be that great. Does that answer? Well, it really depends on the throughput you want, I suppose, because if you have for example, I have a 6-core system, and I have 6 virtual threads that each have to wait 1 second, then you'll only have that many virtual threads running at the same time. So if they all have to, well, switch back, they won't be switching back and forward, so you're really missing the scalability of it all. So I would just, well, the best thing would be to just test it and check if it gives you the scalability that you want. Let's continue. The pooling of virtual threads. You also never ever want to pool virtual threads, because they are that cheap to create. They are really meant to just be disposed of when you are done with them and create a new one when you need to. If you are pulling virtual threads, you, well, are motivated to just change the design to, well, better fit the virtual threads themselves. And of course, you have to look out for all the libraries that may use the unsupported methods, so they might still get pinned. So you have to watch out for that. And then brings us to the part that Ron is going to tell you about. Scoped values.
Yes, thank you, David. Yeah, so virtual threads, they're really easy to use, right? And they're actually so easy to use that it is almost as easy and as cheap as when calling a random method. So it's really not much work for the operating system and for the JVM to do them. So that's an enormous improvement. And actually the spec lead for Project Loom from Oracle, Ron Pressler, he actually said, well, you shouldn't use virtual threads if you just got 10 threads, and actually David's graph showed it. But as soon as you're starting hitting real numbers, thousands, 10,000s or 100,000s of threads, and if you try tonight on your home machine, on your development machine, you will see you will probably be able to run 1,000,000 virtual threads simultaneously. But when we do these things, then we might actually run into different problems with the current Java situation. Now, Project Loom had 3 deliverables. The first one was virtual threads. The second one, which David is going to talk about a bit later, is structured concurrency. And in JDK 20, so the current one, we saw scoped values. And scoped values, they're actually a replacement for thread locals. Now, who of you is familiar with thread locals? That's an amazing number of hands that I see, because when I first came across thread locals, I was really like, what is this? That was really daunting, because let's do a refresher on thread locals. Sometimes you just want to share information between different components of your system. It could be some user credentials that you want to pass on to different parts of your application. It could be something where you want to have a unique trace ID, and in your logging, this unique trace ID should appear. So every component that logs needs to have this information. Now, the best way, of course, would be to just say, okay, I got my methods and I'll add a parameter to them. But sometimes you can't just do that because it's not very scalable. That's one. Sometimes you might execute code from a foreign library, one that isn't yours. So you really don't have the chance to change this. For that, thread locals were introduced in the JDK, I think even in the past century, somewhere in 1999, in JDK 1.1. And the whole idea is, I'm sharing information between different components, and that information that I'm sharing is unique to that specific thread it's running on. So if I would have 2 threads running with different values that I'm storing in there, they couldn't see the value from one another. Underneath, it's just a map where the key to the map is actually the thread. So we share information between components on this level. And the way we do it is that we create a thread instance that can be accessible from anywhere, or at least where you need it. But most likely, thread locals are always like public statics. You provide it with an initial value, and as they are mutable, which, you know, public and mutable is never a good combination, is it? So, but you can mutate the value, which then can easily be retrieved by the different components via a get. Now, let's look at an example. Here we're creating a public static final class thread local for a string type. So it's a typed interface. And we're initializing it with a value. So the first one is initialized, the second one it's initialized with a value. If it is initialized, you can actually set the value, and from any point in your application where you have access to this thread, this value can be set. So in this case, we have this random UID that we're sending somewhere, and somewhere in your code where you would need the value, say for logging, you could actually retrieve it simply with this. Now, this model has worked, and it offers some protection, because if you would, for instance, pass around credentials, well, it would be safer to pass them in a thread local than somewhere else. But there are some problems with thread locals. First of all, this unconstrained mutability. Every part of your system of your current thread can access the values and can change them. So that might be really hard to debug if something goes wrong. And it might also be a bit tricky that maybe pieces of your code that come from an external library actually would have access to them. So maybe not what you want. It also has an unbounded lifetime. David just said, threads, you know, we can use them in executor services. and then executor services, they have this pool of threads in the background, and every time a thread is needed, it will be picked from the pool, it will be sent to run a specific task, and then it is returned to the pool. A classical problem with thread locals, actually, because there's still another method, which is a cleaning method, where you would basically say, oh, you know what, I have this thread local set for my thread, I'm just going to dispose it. I'm going to call the remove method, the value is gone. Very often it was found that didn't happen. So actually this is a kind of memory leakage that you would get. And it would get worse, because the expensive inheritance, if from your current thread, where we say, let's say we have 10 thread locals set there, you would spawn 100 new threads, then every one of these new threads gets their own copy of the thread locals of the original parent thread. So suddenly we would have like 1,000 thread locals around, and they would keep just going around. So while that is a problem in Java with the normal threading, if we're suddenly talking about 1 million virtual threads, then it really becomes a problem. So this is the point where developers said, okay, if we're going to use virtual threads, we're also going to need some new model of passing these values around. Thread local needs to retire. And thread local is going to be retired by using scoped values. Scoped values suddenly, they don't work on a thread basis anymore. They work on a method basis. And they're also immutable. So you can't change the value anymore. Once it is set, that's it. You're not going to get anything else there anymore. Let's look at an example. So we again have the public static final, again, whatever you need, and you're creating a scoped value new instance. We're not setting a value here. Notice we can't set a value here, because the value can only be set once we call a method. So here, what I'm doing, I'm saying scoped value where, and the where is where I'm saying, okay, this is my variable, and it's going to have this value. And the next thing I'm doing is I'm calling the run method. And that run method, that is executing a runnable. By the way, there's also a method for the callable, a call interface. And this scoped value, scoped secret, is only valid within the context of that method. As soon as the runnable here finishes, its values are gone. So that gives us a few advantages. Better memory behavior, because the values will be gone. Also better control, because we know exactly when these values exist and when will they perish. This is another example where you can actually see you can actually cascade the or chain the where methods. So if you want to set multiple values, you can actually set multiple values before you're calling something. And here again you can see the method reference. So as long as the get method is running, these values are available, and afterwards they are gone. So what are the advantages? Immutability increases the clearness of code. Basically, you now know where the values are set, and there's no random place somewhere in your code base where this value might be set, as could be the case with thread locals. Even more importantly, they use references instead of actual values. So this means in the example before, where we had 10 thread locals, so in this case 10 scope values, and we would spawn 100 child threads, they would still all just get 10 references to the original one, so no memory consumption of any severe kind anymore. And finally, when the virtual thread dies, the scoped values die with it. because they're always constrained to a method that was executing. And just to summarize then, thread locals, they will still work with virtual threads. So you can still mix them, you might run into a problem, and that could be the task and the time to change things. Because thread scoped values are more safe, they're more convenient and more scalable. The other thing is true as well. Scoped values work with the current platform thread, so you can actually mix and match the models as you see fit. And if you might think, well, okay, thread locals, I'm not using very many thread locals in my code, so not a worry for me. It actually might not be, but I bet if I would ask here, okay, who's using the Spring module, the Spring Web module for RESTful APIs or something, I bet I would see quite a lot of hands. Spring uses extensively all these these thread locals. So your framework might still be using them. So when combining virtual threads with thread locals, you might still get into problems, and that's also the part where David said that the infrastructure and a whole lot of libraries need to be updated. And I'll guess that's the part where structured concurrency starts.
Thank you. So I got a lot of hands up when people already knew about scoped values. So I was really wondering, who has already heard of structured concurrency? Still quite some hands, that's nice. I hoped for more, but then I get to show you lots of new stuff, which is also really cool. So before I dive deep into what structured concurrency really is, I just want to start very easy and very small with just structured code to show you what the relationships are going to be. So here I have this very simple Java method. This is called method A, and it does two method calls, one to method B, one to method C, and then I have some result that I can return. And the best thing about the structured code is that I can just really easily read from top to bottom what is going to happen when, and what the relationship is between those three methods, the parent method and those two subcalls. So I can just put it in a line and say I'm going to enter method A, then I will execute B, execute C, and then I will have some result that I can return to the parent. So when something happens in the meantime, so I call method A, and while running method B it throws a runtime exception, for example, then at that point in time I know I can stop running this method. I don't have to execute method C. I don't have to try and create some result because I can do it. My method B throw exception, I exit method A, which is all very straightforward. And the same of course goes for method C. If it throws a exception, then I've only ran method B, and method C throws an exception. I'm not going to try and create some result. I will just stop there, and the error will pop up in the with the caller, and then he will solve it. I hope so. So things get a little bit messy when you try to introduce threads, because with threads you have this kind of relationship, this implicit relationship that the threads are going to have, because now I have the same method, but method B and C are both going to use some form of thread that will return me a value later on. So now I have A, method B and C will run in parallel, and then I will have a result. So I will first do the call, wait for the two get methods, and then I will return something to the caller. But then also something happens and method B throws a exception. So the thread running inside B, it will stop working for some reason, it will just throw an exception. But then my thread running in method C will continue running, it will just continue running. Which isn't really that ideal, because when I get at the foo.get, I find out that my method B isn't running anymore, it threw an exception. So now I have to go after method C and try to stop that thread somehow, which is just really annoying. And the same goes if method C throws an exception, but it's just a little bit worse, because if method C throws an exception, I am still running method B. I'm at the foo.get, just waiting till method B has finished. If it takes 5 minutes, I'm waiting there 5 minutes just for it to finish, and then I will do the bar.get, and then I'm like, well, that was very unnecessary because method C has thrown an exception and I could just have exited the method 5 minutes ago, which is just very annoying. And the other thing is if the parent thread just fails, then I will have just 2 threads loose inside my system that I somehow have to, stop if they don't stop themselves, and I even have to notice that this method has stopped. So it isn't really ideal. There is this relationship that I'm really trying to show, but Java isn't really helping me here, and that's where structured concurrency comes into play. And what better way to show you than with a demo? So I'm just going to switch to the second demo. And there you will see something that is called the structured task scope dot shutdown on success. Is it all readable in the back? Thumbs up, great, then I can continue. So structured task scope is Java's way of saying, well, we're going to use structured concurrency. This is the way it's implemented inside Java. And with Java 21, we get 2 shutdown policies. And a shutdown policy is a way of showing what the relationship between my threads is going to be. So I have the shutdown on success, and the shutdown on success policy states that I want to shut down my threads when the first one has finished. So I'm going to create a scope. This scope will be of type shutdown on success, and it will return some type of string, well, just a string. And I'm going to use that same scope object to create or to fork 2 new virtual threads. So when I call the fork method, it will create a virtual thread. It will start running the task that I've given it. In this case, it will just return result 1 or result 2. And then using that same scope, I'm going to call the join. And at this point, my parent thread will block. It will wait till the first thread has finished. The other one will be shut down. And after this has happened, so when my first thread is finished, the code will continue running. And then I can use the result method on the scope to get the result of the first thread is finished. So I don't have to know which one of those 2 threads has finished first. I don't really care about it. But the scope knows which thread finished. So when I run this, in this case, result 2, so the second virtual thread finished first, and the other one will be shut down. So using this policy, I can really easily show, make really explicit what the relationship between my threads are. This is very nice for the person after me who's going to read it, and it just makes managing the lifetime of my virtual threads a lot easier. So we get 2 shutdown policies. The previous one was the shutdown on success, but we also get the on failure. And on failure states that my virtual threads either they all succeed, so they all finish, or if one throws an exception, then the other ones will be shut down. So this, by the way, is also still very much in development. So while some things they'll still change, the ideas behind them will probably be the same. So again, using the scope, I'm going to fork 2 new virtual threads. It will return result 1, result 2. And then I have a type of subject and a subtask. And this subtask, this is my reference to my virtual thread, and later on to the value that I want to retrieve with that virtual thread. And then I do the scope.join. And the scope.join is the same as in the previous example. My parent thread will block until both of my threads either finished successfully or unsuccessfully. But to make it a little bit more exciting, I added the scope.join, the join until. And the join until is like a deadline. In this case, I give both of my threads 10 seconds to finish. If they don't finish in time, I will just shut down. I will just cancel them myself instead. And after they both finished, I can call the throw if failed method. Any throw if failed will rethrow the exception if one has happened inside my threads. So for example, if subtask A would have thrown an exception, I could rethrow it using the throw if failed method, and then the parent thread or the parent, the caller of this method, will know what happened inside the scope. And the best thing is after calling the throw failed, so when I'm at this print line, the best thing about this is that when I reach this, I know that both my threads are finished. Because I'm after the join, no exception has been thrown because I'm after the throw if failed. So at this point in time, I know that both my threads have finished successfully and they are done. And I can just call the get, which will return the value to me. So when I run this, the result will be result 1 and result 2. So that's all there is to it, to structured concurrency. And the pitfall of structured concurrency really is not using it, because otherwise you would have to manage the lifetimes yourself, which is just really messy. You have to write unit tests for them. Nobody likes that, just code you have to maintain, while Java just gives it for free with the structured concurrency. So we've shown a lot today about what you can do with virtual threads, but as we told, we really want you to try and encourage you to try it at home. So all you need is these two methods, the start virtual thread and the new virtual thread per task executor. This is all you gotta know just to start playing and using virtual threads yourself. You can use it using the early access builds already, or with Java 21 in September. So this is all there is to it to get started. And that is the end of this session. Thank you very much for being here. Are there any questions? Yes. If I remember correctly, it's the first exception that's been thrown, because at that point in time it will immediately start shutting down the other threads. So yeah. I would say that it depends on the transaction framework or what the library does with it, because the exception is thrown at that point. Then it just depends on what the transaction, well, how the framework handles it, I would say. Yeah. Yeah. Um, if I remember correctly, an interrupted exception will be thrown inside the virtual thread. So I would say it would just act the same as it would do normally when you're not using threads. So, but I would have to try that out.
I would say so too, because it's actually a checked exception that will probably occur. And well, actually it doesn't really matter if it's checked of non-exception, but exceptions are basically the idea for transaction managers to say, okay, some kind of runtime exception occurred, I'm now going to roll back the transaction. So I would say so too, that the first exception would really roll back all the transactions.
Any other questions? If there's a question right there, I won't see it because the light's really shining in my eyes. Yeah. Could you repeat the question because um, nobody's stopping you from matching the virtual threads with platform threads, but you won't really see the benefit of them if you are just using a small number of virtual threads. Because at that point, the carrier threads, they also get created. So then because by default you will get as many carrier threads as you have cores inside your system. So in this case, I would get 12 carrier threads. So then I would have 12 virtual threads running on 12 carrier threads. So in that case, I could also just use 12 carrier threads directly because they are already there. So with the low numbers, you won't really see a benefit. There is no performance benefit with using virtual threads, except for the scalability part, because you can have create a lot of them, but the virtual threads, they don't run any faster than the platform threads. Their power really lies inside the number and their memory usage. Yeah, that's correct. You don't have to change it, yeah. But what you really want to do is when you have lots of tasks that you want to run on a thread, then it would be better just to adjust to change to your current architecture to fit the use case of virtual threads better, to create just a virtual thread every time you want one. Because with the current platform threads, you're just limited to a amount or just the scheduler. But we really have to make the mind shift from threads being very expensive to very cheap if you're using virtual threads. Does that kind of answer your question? Yeah, it would save you the cost, but yeah, like everything, it depends. You have to really test and check and verify if. Yeah, it's yes. Yes, because I don't know it by heart, but if I remember correctly, it uses um, some. I thought it was some native code. Just they use some primitives. Primitives. They use some primitives, and they didn't know of a better solution yet to make it ready for virtual threads. But as I understand it, it is on the roadmap to be changed in the future. So they are working on it, but it's not ready yet. Yeah, it's. I don't know when. We will have to wait. Yes. Um, it's not. To be honest, I don't have that much experience with Kotlin, but uh, we it looks like just an alternative implementation, and it's just for the Java code bases out there. But yeah, sorry, I don't know much about Kotlin. Yes. Yes, they use a fork join pool, and in that fork join pool, all the carrier threads will run. Any other question? Well, if that's everything, then thank you very much.